We are on the cusp of a technological revolution that could fundamentally alter our understanding of the universe. The evolution of computing has progressed from the cumbersome vacuum tubes of the early 20th century to the transistor-driven digital age that powers our smartphones and supercomputers. Now, we stand at the threshold of a third stage, computing on the scale of atoms themselves. This is the quantum revolution, where the rules of classical physics give way to the strange and powerful principles of quantum mechanics. Quantum computers, already a reality, promise computational power millions of times greater than our most advanced digital systems for specific tasks. These machines are not just faster, they are fundamentally different, capable of solving problems that would take classical computers billions of years to crack. The implications are staggering, and the race is on among tech giants like Google, IBM, Microsoft, and even nations like China to develop the first general-purpose quantum computer, a machine that could reshape industries, economies, and the very fabric of reality itself. Imagine a future where the fundamental properties of matter, such as mass, are no longer fixed constants, but variables we can manipulate with precision. This is not the stuff of science fiction. It's the frontier where quantum computing and artificial intelligence, AI, converge. Google's quantum AI division has already made headlines with its Willow chip, a breakthrough that has physicists whispering about possibilities once thought impossible. From revolutionizing space travel to redefining global security, the fusion of quantum computing and AI could unlock doors to a world where the rules of physics are negotiable. But with such power comes profound responsibility. What does it mean to alter the essence of matter? How close are we to achieving these feats? And are we prepared for the consequences? In this exploration, we'll dive into the science, the breakthroughs, and the warnings from experts like physicist Michio Kaku, uncovering why this moment in history is both exhilarating and deeply unsettling. The journey to quantum computing marks a seismic shift in how we process information. The first computers relied on bulky vacuum tubes and mechanical switches, limited in speed and efficiency. The digital revolution, powered by transistors, gave us the internet, smartphones, and supercomputers capable of performing billions of calculations per second. Now we're entering the quantum era, where computers operate on the principles of quantum mechanics, harnessing the behavior of atoms and subatomic particles. Unlike classical computers, which use binary bits, 0 or 1. Quantum computers use quantum bits, or qubits, which can exist in a superposition of both states simultaneously. This allows them to explore vast solution spaces in parallel, making them exponentially faster for certain tasks, such as factoring large numbers or simulating complex molecular interactions. The global race to build a practical, general-purpose quantum computer is intense. Companies like Google, IBM, and Microsoft are investing billions, while nations like China are prioritizing quantum research to gain a strategic edge. The stakes are high. A fully realized quantum computer could crack encryption systems, optimize global logistics, and accelerate drug discovery. But it's Google's quantum AI division that has recently captured the world's attention with a breakthrough that defies expectations. The Willow quantum chip, unveiled in December 2024, is not just a step forward. It's a leap into uncharted territory, raising questions about the very nature of reality and our ability to control the technologies we create. In late 2024, Google introduced the Willow quantum chip, a 105-qubit processor that has redefined the boundaries of computational power. This chip performed a benchmark calculation in just under 5 minutes, a task that would take the world's most powerful classical supercomputers an estimated 10 to the power of 25 years to complete. To put that in perspective, 10 to the 25th power years is longer than the age of the universe itself, which is roughly 13.8 billion years. This achievement is not a mere incremental improvement. It's a paradigm shift that demonstrates the raw power of quantum computing. The Willow chip leverages quantum phenomena like superposition, entanglement, and tunneling to process information in ways that classical computers simply cannot match. The implications of this breakthrough are profound. The Willow chip can simulate complex quantum systems, optimize algorithms, and design materials with unprecedented precision. But what has scientists and engineers buzzing is the possibility that quantum AI, powered by chips like Willow, could go beyond computation to manipulate the fundamental properties of matter, specifically mass. By combining quantum computing with advanced AI algorithms, Google is pushing the boundaries of what's possible, exploring scenarios where the rules of physics might be rewritten. This convergence of technologies is not just about faster computers, it's about unlocking the potential to reshape the physical world in ways we've never imagined. When we think of mass, we imagine something tangible, the weight of an object, the resistance it offers when pushed. In physics, mass is the property that gives an object inertia, its resistance to acceleration, and it's determined by how strongly particles interact with the Higgs field, an invisible energy field that permeates all of space. Electrons, for example, have less mass than quarks because they couple less strongly to this field. But what if we could alter these interactions or create materials where particles behave as if they have no mass at all? These ideas, once confined to the realm of theoretical physics, are now being tested in laboratories worldwide, and quantum AI is accelerating the pace of discovery. Google's Willow chip, combined with advanced AI, is enabling scientists to simulate complex quantum systems and design experiments that push the boundaries of physics. The notion of mass as a programmable variable is no longer pure fantasy. Researchers are already creating systems where particles exhibit altered effective mass, the mass they appear to have under specific conditions. These advancements suggest that we may be on the verge of a new era where the fundamental properties of matter can be manipulated, opening doors to applications that could transform technology, energy, and even our understanding of the universe itself. The concept of manipulating mass is not just theoretical. Scientists have already achieved remarkable feats in altering how particles behave. At the University of Pennsylvania, researchers have developed metamaterials, artificially engineered structures, where electrons move as if they have near zero mass in certain directions. These materials defy conventional physics, allowing electrons to travel with virtually no resistance, which could lead to breakthroughs in electronics and energy storage. In other laboratories, scientists have created Bose-Einstein condensates, ultra-cold quantum fluids that exhibit negative effective mass. When pushed, these fluids accelerate in the opposite direction of the applied force, challenging our intuitive understanding of motion. Another fascinating example is the Casimir effect, which demonstrates that the vacuum of space is not empty but filled with virtual particles and energy fluctuations. By placing two uncharged metal plates close together, scientists can manipulate this vacuum energy, creating measurable forces. These experiments show that we can influence the inertial properties of matter in localized regions. While these breakthroughs were achieved without the full integration of quantum AI, they hint at the possibilities when systems like Google's Willow chip are fully deployed. By simulating complex quantum interactions, quantum AI could design materials or configurations that push these phenomena further, potentially making mass a tunable property. Google's quantum AI is exploring uncharted territories where the fundamental properties of matter could be reconfigured. One pathway involves tuning how particles couple with the Higgs field, the energy field responsible for giving particles their rest mass. If quantum AI could model and manipulate these interactions, it might allow us to adjust an object's mass without changing its physical composition. This remains speculative, but the ability to simulate Higgs field dynamics could uncover new physics that makes such tuning feasible. Another avenue is vacuum engineering, where the bubbling sea of virtual particles in empty space could be manipulated. The Casimir effect already shows that we can alter vacuum energy by changing the geometry of physical systems. Quantum AI could design configurations that shift vacuum energy density in localized regions, creating pockets where inertial properties change. This could lead to environments where objects behave as if they have altered mass, with applications in propulsion and energy generation. Additionally, quantum AI could accelerate the development of metamaterials, creating substances where particles respond to forces in ways that defy conventional physics, such as exhibiting zero or negative effective mass. Einstein's theory of general relativity offers another possibility through frame dragging, where mass warps spacetime. Quantum AI could simulate localized spacetime curvature effects, potentially altering how objects experience inertia. Finally, by modeling complex quantum field theories like lattice gauge theories, AI might discover new types of particles or states of matter with tunable mass properties. These pathways, while theoretical, are becoming increasingly plausible as quantum AI systems grow more powerful, raising the question of what happens when these possibilities become reality. Renowned physicist Michio Kaku has described the fusion of quantum computing and AI as a historic revolution, a moment that could redefine technology and society. But he also issues a stark warning: as machines become capable of learning and evolving beyond their initial programming, our ability to control them diminishes. When quantum AI begins to explore the fundamental properties of matter, such as mass, we enter a realm where the consequences are unpredictable. Kaku's concern is not about the technology itself, but about about its autonomy. If AI systems start designing experiments or configurations that manipulate physical properties in ways we don't fully understand, we risk losing control over the outcomes. The implications of mass manipulation are both thrilling and daunting. Spacecraft that adjust their inertial properties could achieve unprecedented speeds, transforming space exploration. Technologies that alter effective mass could revolutionize ballistics, creating projectiles that shift mass mid-flight or defensive systems that render objects effectively weightless. Since mass influences gravitational fields, and gravity affects time dilation, manipulating mass could even create regions where time flows differently. However, these advancements carry risks. Some physicists warn that tampering with fundamental fields, like the Higgs field, could trigger catastrophic scenarios such as vacuum decay, where a bubble of altered vacuum state expands at the speed of light, potentially rewriting the laws of physics. While speculative, these warnings underscore the need for caution as we push these boundaries. The line between simulation and reality is increasingly indistinct. Quantum AI systems like Google's Willow chip excel at modeling quantum fields and interactions that classical computers cannot handle. These simulations are no longer abstract, they're driving real-world experiments. For example, researchers at the University of Pennsylvania used conventional methods to create metamaterials where electrons behave as if they have zero mass. Bose-Einstein condensates have demonstrated negative effective mass, accelerating against applied forces. These breakthroughs, achieved without quantum AI, hint at what's possible when AI takes the lead. Quantum AI can explore parameter spaces that no human could navigate, designing experiments and materials with unprecedented precision. As these systems scale up, they could model Higgs-like vacuum configurations or complex field interactions, uncovering patterns that suggest new ways to manipulate matter. The simulations of today could become the blueprints for tomorrow's technologies, potentially allowing us to engineer environments where effective mass is a tunable variable. However, if quantum AI identifies configurations that push physics beyond our current understanding, we may inadvertently create systems with consequences we can't predict, highlighting the need to maintain human oversight as we transition from simulation to implementation. The ability to manipulate mass, even in localized or effective ways, could trigger a geopolitical earthquake. Systems that intensify or reduce gravitational effects could disable vehicles or infrastructure without conventional explosives, transforming military capabilities. Materials with programmable mass properties could bend light in ways that make objects undetectable, redefining stealth technology. AI-built projectiles that shift mass mid-flight could achieve unprecedented range and impact, rendering traditional defenses obsolete. These advancements could upend global security, creating a strategic imbalance that demands international cooperation. Beyond military applications, mass manipulation could revolutionize energy production, transportation, and construction. Buildings made of materials with tunable mass could reduce construction costs, while vehicles that adjust their inertia could maximize efficiency. These advancements could transform human civilization, addressing challenges like resource scarcity and climate change. However, they also introduce risks if they become part of a global arms race. The race to control quantum AI and its applications is already underway, with nations like China and the United States investing heavily. Without ethical frameworks and global agreements, the pursuit of mass manipulation could lead to destabilization or unintended consequences. To understand the possibilities of mass manipulation, we must ground ourselves in the science of mass. Physicists distinguish between rest mass, the intrinsic mass of a particle at rest, determined by its interaction with the Higgs field, and effective mass, which describes how particles behave in specific materials or fields. The Higgs field, discovered in 2012, is an energy field that gives particles their resistance to acceleration. Einstein's equation, E equals mc squared, shows that mass and energy are interchangeable, as seen in the sun's fusion process, which converts 0.7% of hydrogen's mass into energy every second. While altering fundamental rest mass remains beyond our reach, manipulating effective mass is already possible. The Casimir effect demonstrates that vacuum energy can be modified, creating forces that could affect particle behavior. Bose-Einstein condensates exhibit negative effective mass, defying conventional motion. Metamaterials allow electrons to move as if weightless, opening new possibilities in electronics and optics. Quantum AI could take these experiments further, designing systems with properties we haven't yet imagined, blurring the line between fundamental physics and technological innovation. As quantum AI pushes the boundaries of physics, we must confront the ethical implications. The ability to manipulate mass raises questions about responsibility and control. How do we ensure that these technologies benefit humanity rather than causing harm? How do we prevent a global arms race that could destabilize the world? International cooperation is essential, just as nuclear technology prompted treaties and safeguards. Ethical frameworks must address autonomy, transparency, and accountability, ensuring that AI systems remain under human oversight. Education and public engagement are critical. The public must understand the stakes of these technologies to demand responsible development. Scientists, policymakers, and industry leaders must work together to balance innovation with caution, ensuring that we harness the potential of quantum AI without crossing boundaries that could lead to catastrophe. The choices we make today will shape not only our technological future, but also the kind of world we leave for future generations. The implications of quantum AI and mass manipulation extend far beyond science and technology, promising to reshape society itself. If mass can be tuned, the energy costs of transportation could plummet, making global travel more accessible and sustainable. Cities could be built with materials that adapt their properties to environmental conditions, reducing waste and enhancing resilience. Healthcare could see breakthroughs, with quantum AI designing drug delivery systems that manipulate molecular interactions at unprecedented scales. These advancements could democratize access to resources, improve quality of life, and address global challenges like climate change and resource scarcity. However, they also demand a reevaluation of economic systems, as industries built on traditional materials and energy sources could face disruption. Society must prepare for a future where physical constraints are no longer fixed, ensuring that these technologies benefit all rather than deepening inequalities. As we stand on the cusp of manipulating mass and rewriting the rules of physics, we must grapple with profound philosophical questions. If the fundamental properties of reality become malleable, what does it mean to be human in a world where constants are no longer certain? Quantum AI's ability to alter the fabric of space-time challenges our understanding of existence, free will, and our place in the universe. Are we creators, stewards, or mere passengers in this new era? These questions demand introspection and dialogue, as the choices we make today will shape not only our technological future, but also the essence of human identity. As we venture into this uncharted territory, we must balance the pursuit of knowledge with humility, recognizing that the power to reshape reality carries the weight of redefining who we are. The potential to manipulate mass through quantum AI could usher in a new era of environmental sustainability, fundamentally altering how we interact with the planet's resources. Imagine transportation systems where vehicles adjust their inertial properties to minimize energy consumption, drastically reducing carbon emissions and dependence on fossil fuels. Construction could be revolutionized with materials that dynamically adjust their mass to optimize structural integrity while minimizing resource use, enabling eco-friendly skyscrapers and infrastructure that adapt to changing environmental conditions. Quantum AI could also optimize energy production, designing systems that harness vacuum energy or other quantum phenomena to generate power with minimal environmental impact. These advancements could address pressing global challenges like climate change and resource depletion, offering a path toward a more sustainable future. However, the environmental benefits must be weighed against the risks of scaling these technologies too quickly, as unintended ecological consequences could arise from manipulating fundamental physical properties without fully understanding their long-term effects. Responsible development and rigorous testing will be essential to ensure that quantum AI's environmental promise is realized without compromising the planet's delicate balance. The advent of quantum AI and mass manipulation will not only transform technology and society, but also catalyze profound cultural shifts. As the boundaries of physics become malleable, our collective imagination will expand, influencing art, literature, and philosophy in unprecedented ways. Artists may explore new mediums that reflect the fluidity of mass and space-time, creating works that challenge our perceptions of reality. Literature could see a resurgence of speculative fiction, grappling with themes of human identity in a world where physical constants are negotiable. Cultural narratives around progress, power, and responsibility will shift as societies grapple with the implications of technologies that blur the line between the possible and the impossible. This cultural evolution will require global dialogue to ensure that diverse perspectives shape the ethical frameworks governing these technologies. By fostering a culture of curiosity and accountability, we can harness quantum AI to inspire creativity and unity while guarding against the hubris of wielding power over the fundamental forces of nature. Google's Willow quantum chip is a window into a future where the laws of physics are no longer fixed but negotiable. The convergence of quantum computing and AI is unlocking possibilities once confined to science fiction, materials with tunable mass, propulsion systems that defy inertia, and environments where time itself flows differently. But with these possibilities come profound responsibilities. Michio Kaku's warning reminds us that we are entering uncharted territory where the power to manipulate matter could transform our world or destabilize it. As we stand on the brink of this quantum future, we must ask, are we ready to rewrite the rules of reality? And can